And we are now recording. Some little spot has gotten on the screen. I want to make sure I can get it off. There, I think I got rid of it. Okay. All right, today, if there are no questions or anything we've done so far, just a quick review. We finished chapter 8, and I gave you the test for chapter 8. Hopefully y'all are working on that too, as well as the research papers. Good comment there, Houston. We went through sections 1 and 2 in chapter 9. We finished those, and we started in 10.2 in chapter 10. In chapter 10, we're only going to do 10.2, 10.3, and 10.4. And then will be time for the second test. So we're in 10.2 now. We're going to be going, if we finish 10.2 today, we'll start 10.3. So that means it could be you'll be ready for the second test as early as the end of next week, beginning of the following week. So that's just a little hint. Try to keep things moving. I've got to get things moving too, because I've gotten so far behind because of all the weird things that have been happening this term. The new banner, the new this, that, and the other thing, new way to do everything's been new, and they keep piling stuff on top of stuff on top of stuff. And I've finally at the point where I've got almost everything in Blackboard printed, but I've still got to go back and do emails. I had them caught up over the weekend, but now I've gotten behind this week, so I've got to get those printed. And at that point, then I'm going to start grading, okay? And then I'll be grading like crazy. Remind me to make an announcement. Well, no, I'm sorry. That was my first class. I should have made that announcement too, and I forgot. But I will send them a message, I guess. So anyway, unless there's some questions, we're in chapter 10, conics, which we're not doing conics, parametric equations, and polar coordinates. We are doing the last two. 10.2 is plane curves and parametric equations. We're on the top of page 703, and this is example 3. Now, example 3 is not given on the PowerPoint, obviously, but it is given at larsoncalculus.com. You can go there for an interactive version of this type of an example. So let me get my Wacom pad, and let's see. Sketch the curve represented by x is equal to 3 cosine theta y is equal to 4 sine theta. Okay, and we're going to sketch this between, as theta is going from 0, theta going from 0 to 2 pi. Okay. Now again, I kind of like to do a version of the t-table. In this case, it's going to be maybe a theta table. So we're going to have thetas here. I'll just do columns. X is here, and Y is here. Okay. Give me a theta between 0 and 2 pi. How about 0? Cosine of 0, anyone tell me what that is? 1. Okay, good. And 1 times 3 is 3. Okay. Sine of 0 is 0, and 4 times 0 is 0. Okay. Now, that's the most convenient one. I'd say let's skip on over to pi halves. That's a nice one. What's the cosine of pi halves? I forgot to write down theta is equal to pi halves. What's cosine of pi halves? Zero. 3 times 0 is 0. What's the sine of pi halves? One. Okay. 4 times 1 is 4. Okay. Let's go on to pi. This may not be enough points, but it'll be enough to get us started. Okay. Cosine of pi is -1. And 3 times -1 is -3. Sine of pi is 0, and 4 times 0 is 0. Let's go down to 3 halves pi. Cosine of 3 halves pi is 0, and 3 times 0 is 0. Sine of 3 halves pi is sine of 3 halves pi, -1. 4 times that is -4. And then let's round it up at 2 pi. Like I say, we might need some in between, but we'll get started with these. Cosine of 2 pi is 1, and 3 times 1 is 3. Sine of 2 pi is 0 times 4 is 0. All right, let's get our axes going here. Okay, and we're going to need on the y's go up to and down to 4. So that would be 2 and 2 and 1 and 3 and 1 and 3. And the x's are only going 1, 2, 2, 3. -1, -2, -3. So the first place, x is 0, x is 3, y is 0. That's right here. That's when theta is equal to 0. Now, as theta increases, we'll go on and plot the next point. As theta, we go up to pi halves, your x is 0 and your y is 4. So we're up here. Now, how do we get there? You're increasing, your x's were decreasing in value at the same time your y was increasing in value. Everything was positive there. So basically you have a shape that looks something like that. Now, I don't draw these well. Something like that. Not exactly, but something like that. And then when theta is equal to pi, your x is -3 over here, y is 0 here. And what was happening, yuck, this is so aggravating. Okay, what was happening there, your x's were decreasing toward -3, and your y's were also decreasing to 0. Okay, so therefore you're going in this direction here. All right, and then at 3 halves pi, your x is 0, your y is -4. Your x has now started increasing again from -3 to 0. Your y's are decreasing from 0 to -4. So this looks something like that. This is not coming out well. Okay, and then you go back to the original place and your x's are increasing, y's are increasing, and there you have it. Now what that's supposed to be is an ellipse. And by the way, our direction, because with parametric equations you always have an orientation. Oh, here's someone coming in. I can't see who the name is. Let's see if I can catch them. It's Laron. All right. So Laron is here. Hold on a moment. Let me get my book. And let me mark Laron marked present. I can't get my pen to operate. This is okay. All right. 4 out of, what is it? 4 out of 8. So we're half of us here. Well, we've lost somebody, haven't we? I had James and we've lost James. So hopefully he'll be back. Welcome, Laron. Okay, we're in chapter 10. We're not doing the conics part, that was 10.1, so we're doing parametric equations and polar coordinates. We're right now on the parametric equations part, and that's in 10.2, which is plane curves and parametric equations. We're doing example 3 on page 703. We've just now got it sort of sketched, not as nicely as perhaps the book is, but we've got it sketched. Okay, now I didn't read the whole problem. Sorry about that, folks. What I did, I said sketch the curve represented by x equal that, y is equal that, and theta equal that, and I started sketching. What I didn't read, it says by eliminating the parameter and finding the corresponding rectangular equation. Whoops! I didn't do it that way. I sketched the curve just as given. So let's do what they're suggesting, which is sketching it by eliminating. Okay, now this is not going to be super easy to eliminate like it is with an XY form. Okay, it's easy enough, but it's just not quite as good as, say, polynomials or especially linear functions and things like that. So how can we eliminate the parameter? Okay, well, here's what they do. Let's solve it not for theta, but for cosine theta and for sine theta, okay? Because we know a very special relationship there. So what we know is that cosine theta, by dividing both sides by 3, someone else coming in? I don't see them, okay? You get that cosine theta is equal to x over 3. Same thing up here. Let's solve for sine theta, dividing both sides by 4. And we get that sine theta is equal to x over 4. The pen's not writing well. It'll skip where it wants to skip and then suddenly start writing where I don't want it to. So it's kind of weird. Okay, now, not particularly easy to solve for theta here, but here's something we do know. All of you should know. Your good old Pythagorean identity, sine. Anyone remember that? Oh, here comes somebody. James is back. Good deal. Welcome back, James. I don't know if you can hear me yet, but okay. See, now the pen's writing other places, okay? So this is sine squared theta plus cosine squared theta. We know that's always equal to 1, don't we? But sine is x over 4, so this is x squared over 4 plus cosine is x squared over 4 squared. Sorry, you were going to let me get away with that, weren't you? Cosine theta is x over 3. I'm sorry. Y'all let me get away with that too. This is y over 4. So that's a y squared over 4. Y'all are not catching me at anything here. You're leaving me out here to dry. And cosine is x squared over, I'm going to write it 9 this time, and that's equal to 1. So here's a 16. Oh, here's somebody else coming in. I can't see who it is. Oh, Jemanuel. Good deal. Let's admit Jemanuel. And now we're up to 5 students. Yes. So we broke the halfway point. Jemanuel is here. All right. We've got 3 to go. That's Esther, Kyle, and Jesus. So hopefully they'll be coming in at some point. I know you probably have heard this before, but Kyle had tested positive for COVID, so he had to be quarantined for 2 weeks. I think his 2 weeks was over today, so it may be that he's having to go in for more testing today, because he, I think, was supposed to rejoin the baseball team today, but they probably required a clean test. So I don't know. I'm just making a guess there. That may be why we don't see Kyle today, but hopefully he'll be showing up. Okay, someone else coming in. I don't see them now. Okay, so this is a y-squared. Let me see if I can clean that up some. Y'all let me get away with writing things poorly. This is so aggravating. I go to erase and it just changes to a different functionality. Okay, so this is y squared over 4 plus, okay, so that's y squared over 16 plus x squared over 9 is equal to 1. Well, what's the common denominator between 16 and 9? Boy, that's a tough one, isn't it? But actually we don't need to do that. Okay, let me rewrite this. In fact, let me go back and write it the way I was starting to write it before. And this is where it sort of hurts that we didn't do the conics. This form, I'm going to reorder it. X squared over 3 squared plus y squared over 4 squared is equal to 1. That is the equation of an ellipse whose minor axis is 3 plus or minus 3, major axis plus or minus 4. Okay, that's an ellipse, and that's exactly what we got written here. The problem is when you do it in XY terms in rectangular coordinates like this, you don't have the orientation. When you do it in the parametric equations like this, you can determine the orientation. That's going counterclockwise. So I like the way we did it better than they, but I wasn't reading the question well. Okay. Now, so they drew the arrows in even though they supposedly graphed it off the other. They had to go back to the parametric equation and note that it was going counterclockwise. Okay. There is some stuff at the bottom of that page, and I'm trying to see if it's really all that important. And it looks like they're just doing everything twice here, and I can't figure out why. I swear those two things. Oh, I'm sorry. Okay, I see the difference now. Okay. And this is probably worth noting. Okay. And I think we're going to have to note it on another page. Any questions on this before I erase it? So I'm going to clear the drawings here. And here's what they are saying. If you have a parametric equation such as this, x is equal to h plus a cosine theta. First parametric equation. Second one is this one, y is equal to k. This aggravates me. Times plus b. Whoops, here's comes somebody in. Here is Kyle. I don't know if I can get him in here because it's covering him. There's Kyle. Admit him. Okay. Kyle's here.
Sorry I'm late.
No problem. Did you get released today?
No, I have to go to an appointment tomorrow, and hopefully get released tomorrow.
Yeah. So is that to have a new test or what?
Well, no, they're not testing me. They're just doing a checkup, I guess.
I see.
They're not going to find anything because I'm feeling great. But.
Good, good. Okay. Well, glad you recovered so nicely. And that it didn't sound like it was too awful bad while it was happening, but I guess it was bad enough, wasn't it?
No, it was very mild, but
yeah.
I'm thankful it was just mild.
Yeah, how's your roommate doing?
He's doing great. He has no symptoms. He has to get tested tomorrow, though. So.
Yeah, I figured he probably would. Okay. Okay, so you just have a checkup and he gets tested. Okay. Well, welcome back. I'm glad you're here. Okay. We're doing example 3 on, well, actually, we've done example 3 on page 703. We're in chapter 10. We're not doing the conics part. We're doing parametric equations of polar coordinates. We're on the parametric equations part, 10.2, plane curves and parametric equations. Okay. We've just done example 3, which is not on the PowerPoint, so we did it on the whiteboard. But it's also at larsoncalculus.com, so if you want to see them do it, you can watch that there. We're on the bottom part of 703, which is saying this, okay? I was just writing it down now. X is equal to h plus a cosine theta, y is equal to k plus b sine theta, okay? And theta is going from 0 to 2 pi. That's very similar to the problem we just had, with one, it's actually a little more complicated. We didn't have the h and the k. We just had zeros there. So that was an ellipse centered at the origin. Okay? When you put the h and k in there, all that does is translate the x to the right and translate, if h is positive, and translates the y. Okay, here's somebody else. Hey, Jesus is coming in. Good deal. We are going to have a decent class today. I mean, it's already decent, but we're going to have an almost full class. We're only missing Esther. Has anyone heard from Esther at all lately? We got her in the class and then haven't, well, maybe seen her once since then and not. So I hope she's okay. Has anyone heard? Okay. All right. So what we have here, all it's doing is translating x in whichever direction h is. If h is positive, it goes to the right. And then if k is positive, it goes up. If k is negative, it goes down. H negative, it goes that way. So anyway, we've just shifted that ellipse to a center of hk. Exactly what we did before. Okay? And that's traced counterclockwise because your cosine starts maximum x and then starts going negative until it gets to the minimum x, and then starts going positive again until it gets back to maximum x. Whereas the y starts at 0 and starts going up in y, then down, and then back up again. So the combination of those two takes you in a counterclockwise direction. Now, another way to express that is this, and I don't know if this is completely clear to you. But if you were to solve this for cosine theta and that for sine theta like we did in the problem, and then square it, add them and get 1, what you wind up with is x minus h over a squared, that's your cosine squared, plus y minus k over b squared, and that would be equal to 1. Okay? Because sine squared plus cosine squared is 1. Well, that is an ellipse whose the x is these are called major and minor axes, depending on which is larger, A or B, and we usually take those to be positive numbers. Whichever is larger is your major axis, and if A is larger than B, then your major axis is on the x-axis. If B is larger than A, then your major axis is on the y-axis, like the problem that we just did was. But it's shifted to wherever HK is. If H is positive and K is positive, it's shifted up in the first quadrant. If H was negative and K is positive, you're in the second quadrant. If X was negative and Y and K is negative, you're down in the third quadrant. If H was positive and K negative, the center is down in the fourth quadrant. It could be the ellipse goes, crosses over. Okay, now, but that's going counterclockwise. If you turn things around ever so slightly, x is equal to, keep the h, plus a sine theta, okay, and y is equal to k plus b cosine theta. So all you've done, whoops, here comes somebody. Could it be Esther? Yes, she's here. Fantastic. Speak of her and she shows up. Okay, perfect attendance today, folks. Way to go. Way to go. Everybody's here. Makes my Wednesday. Okay. Oh, I lost my pen too. So welcome, Esther. I don't know if you can hear us yet, but I'm glad you're here. Okay. We're in chapter 10. Now, chapter 10 covers conics. We're not covering that. That was 10.1. We're starting in 10.2, which is where we are now, plane curves and parametric equations. So the parametric equations part of chapter 10. And then later we'll do polar coordinates. Okay? So actually 10.2 and 10.3 are parametric equations. 10.4 is polar coordinates. So we're doing 10.2, 10.3, and 10.4. We just finished 9.1 and 9.2. And when we finish 10.3, then we'll have a test on chapters 9 and 10. Only on 9, 1 and 2, and 10, 2, 3, and 4. So covering 5 sections, and that will be your test 2. The test 1, by the way, folks, is already out there. And I can't remember now whether I put it in 2 places or 1. I know I put it as a message on Blackboard Messages. I can't remember if I put it as test 1 somewhere around week 4, wasn't it? I believe it was week 4. What I don't know about that, whoever set up these these templates, they were not very consistent with them and a little bit sloppy. And occasionally they didn't leave us a plus sign that we can put something in there. They just put the template there and we can't do anything with it. If they put the little plus sign, that means we can click on that and add our material. Some of them they did, some of them they didn't. I just don't remember in this class whether it was there or not. So if you don't see it in, I believe it was week 4, then don't sweat it. You might see test 1 listed there, but you might not see it loaded in that place, but it's always loaded under messages. If it is loaded there, you can pick it up either place. It's the same test. But that's test 4. That was the chapter let me think back, chapter 8 test. Okay, and then 9 and 10 will be together. We're only doing 5 sections between these 2 chapters, and that will be the second test. So try to get the first test in before we finish 10.3. No, 10.4. Good buddy. Okay. Now, if we do the same thing we were doing up here and subtract the h and the k from both sides of their equations, then divide by a and b, what you have then is that x minus h over a, okay, that would be your sine theta. Square that, okay, plus y minus k over b. This looks exactly the same, squared, is equal to 1. So these two look identical. The rectangular plot is identically the same. So what's the difference? Well, let's think about your action. Oh, I forgot to write this part down, which is important. 0 is less than or equal to theta is less than or equal to 2 pi. Same as before. So why mess with writing it? Well, now, here's where we do our evaluation. See, your x now, when theta is equal to 0, the sine is 0. So you're starting at h, and when theta is 0, cosine is 1. So you're starting there at k plus b. K you already had, and then you're adding b. And then as theta increases, sine is going more positive, cosine is going more negative. So now you're not going in the counterclockwise direction, you're going in the clockwise. So this may be an ellipse like this. In the counterclockwise direction, it'll be that same ellipse here, but going in the clockwise direction. The center is the same, HK, in both of them. The major minor axes are the same, the A's and the B's. Whoever's the largest, that's going to be the major axis. I drew them as if Y is the major axis. So you'd be going from K here, you would be going up B and down B. No, yeah. No, that's not right. Yeah. And the H's are going, the X's are going, starting with H, you're going left to right, B units. So A would be how far you are from the center, from H, in that direction. B would be how far you were from the center K in the vertical direction. So that's the only difference. It's exactly the same ellipse, only the one that starts where X is cosine, you're starting over here going counterclockwise when X is sine, and Y is cosine, you're starting here and going clockwise. Okay. I don't know if that was worth spending that much time on, but we did it. Okay. So I think I can get this hot book out of my lap and maybe put away the Wacom for a moment here and go out of this, or actually go into our 10.2. Okay. That was the end of example 2. We just did example 3. Let's get the slideshow set up from example 2, the end of that. Now we're going into, this is on page 704, finding parametric equations. Now if you think about what we were doing before, we were given a set of parametric equations, we found the curve. Now we're being told what the curve is, you find the parametric equation. The first 3 examples in the section illustrate techniques for sketching the graph represented by a set of, well, let's see, it probably is, yeah. Here's example 4. Let's just jump into the example. Find the set of parametric equations, okay, that represent the graph of y is equal to 1 minus x squared using each of the following parameters, okay. I wish they hadn't said this. In fact, I think I'm going back to here. Let's just go back to our whiteboard. We're going to do this without them telling us what to do. I don't like to be told what to do, right? Okay. Find the set of parametric equations that represents this graph. Y is equal to 1 minus x squared okay, using, and it says each of the following parameters. We'll hold off of that. Let's just do it the simple way. Now here's what my first off-the-cuff suggestion would be to do. Find the more complicated variable in this problem. Which is the more complicated one? I think it's pretty obvious. It's x. Let's let that be our parameter. Now, do you have a preference on what you want to name the parameter? The book used t. So are you happy with t? That's the favorite parameter, just like x is the favorite variable, t is the favorite parameter. Let t equal x, or x equal t. I don't care which way you say it. Now, knowing that, let's figure out what y is. Y is equal to, that's why we use the more complicated one here, 1 minus, but x is t, t squared. There's your parametric equations. X equal t, y is equal to 1 minus t squared. Done. Done. That's it. That's all. You found your set of parametric equations. The x equal t, y is equal to 1 minus t squared. That's it. Okay? Now, the second thing they said to do was, let's use it, find the set of parametric equations that this is the condition. Well, I chose the easy one, and that's what they had you do first, x equal t. Only they said t equal x. Same thing, okay? This time they say the slope, m, is basically your first derivative, dy dx, okay, at any point xy, okay? That's going to be your parameter m. Well, guess what we're going to do? Take the equation and do dy dx. Take the derivative of y. And since this is calculus class, you can do that. What is dx, dy dx? Minus 2x, right? Okay. Now, and this is our m. Well, from that we can see, divide both sides by minus 2, and you get x is equal to, that's a minus 2, minus m over 2. Okay? And once we have that, we can plug that in here. So y is equal to 1 minus, and when you square a minus m over 2, you get m squared over 4. So there's your y. X equal this, y is equal that. There your parameter is your derivative, or your slope, m. Okay? So x equal m over 2, y is equal to 1 minus m squared over 4. That's the set of parametric equations. Guess what? It gives you the same curve no matter what's happening. Now, the direction may vary. I don't know. I haven't jumped into that one. I would say it would, because the x here is a negative, what your parameter is. X is positive, what your parameter is here. So my guess, one of these might be going, and by the way, this is a parabola. You recognize that. It's opening downward. One of them's going one way, one of them's going the other way, in my mind. Okay? The one that's going from right to left, that parabola, that's the one with the M. The other one I think is going left to right. Okay. So I think that's all. Okay, well, let's go back and see how they did the problem. I forgot they did it. I should have let them do it. Okay. Let's go back to the original, back to our current slide. And here's what they are. I already told you, the easiest parameter is choose the more complicated variable, let that be your parameter t or whatever you want to call it, and then plug and chug. Okay? The second one was a bit bizarre. You did an operation to get your parameter dy dx and then plug that in and see what you get. So the first one, let x equal t, that produces a parametric equation. Y is equal 1 minus x squared would be y is equal to 1 minus t squared. So there are your two equations. Here's the first one, x equal t. Here's the second one, y is equal to 1 minus t squared. That's it. Done. Now to do the next one, write x and y in terms of parameter m, you proceed as follows. Take the derivative. Okay? That was m is equal to minus 2x. Now at this point, there's your parameter. Solve for x. Okay? And when you do that, you get x equal minus m over 2. And then you plug that into this equation here, and you get y is equal to 1 minus a negative m over 2 squared, which is 1 minus m squared over 4. Sorry, I'm having trouble talking. I was able to cram down just a little bit of lunch in between my first two classes. And I did not drink enough, so I'm going to have to keep hydrating here for a bit. There's that, and there's also the fact this is fall allergy season, and though I've never been a big one on allergies, I think in my older age I'm getting worse at it. So there is your second parametric equation. The first one is x is equal to m minus m over 2. Where in the world is my pen? There it is. There's the first parametric equation. There's the second one. It's not letting me underline it, so I'll circle it. I'll circle this one too. So that's a couple ways. This was a weird one, but you can find parametric equations a variety of ways. So this parametric equation plots like this. Note the resulting curve has a right to left orientation determined by increasing values of the slope. Because you're going from a positive slope, and then start going negative slope, negative slope. Actually, it's a decreasing values of m because m is minus 4, up here is minus 2. Oh no, this is increasing. Okay, sorry. That's backward though. Oh, okay. Your slope here is negative. Okay. Negative, the slope is negative, so it's minus 4 here, minus 2 here, 0 here, plus 2 here. Don't follow the arrows here. What way is your slope of your curve at that point, the tangent point? It's going upward. So that's a 2, 4, and so on. So yeah. So that's, again, just an odd way to choose your parametric equation, but it works. It works perfectly fine. Now, example 5 is at the top of the next page. Determine the curve traced by point P on the circumference of a circle of radius A rolling along a straight line in a plane. What? Okay. Hopefully they're going to draw the graph for you. Not yet. Now, without parametric equation, that is one bear of a problem. Okay? Even with parametric equations, it's still somewhat bearish. Okay? Let the parameter theta be a measure of the circle's rotation. So what we're starting with, and I wish they had drawn the picture already, you're starting with a circle. Okay? And that circle is going to start rolling in a line on a plane. We'll say from left to right. And if you start that point on that circle to be at the origin when you're starting it, and you start that circle rolling, then that point's going to pick up a little bit, and then it gets to be one diameter high, and then it starts coming down, and then it picks up and goes again. So what you have is sort of a, this is a weird way to say it, an upside down sawtooth pattern, kinda. Not really a sawtooth, but that kind of thing. So you have a curve here, another curve, another curve, another curve. Okay? That curve is called a cycloid. So the parameter theta is a measure of the circle's rotation. So taken from the center of the circle, and we'll start with it down, okay, and it's rotating, that's your theta. And let P equal XY be at the origin, begin at the origin, so you're starting down there. Let's see if they finally will show you a picture. When theta is equal to 0, P is the origin. X and Y are both 0. Okay, got it. When theta is equal to pi, P is at a maximum. So you've turned from down here, theta equals 0 here. It's hard for me to do it. I wish they had the picture already. And then when you turn exactly pi, so it's going from down to straight up, now you're at a maximum point. And that maximum point is P times A, that's the X distance. I mean pi times A is the X distance, and 2A is the Y distance. Okay? So let's see that. Oh, goodness gracious. And when theta is 2 pi, you're back at the origin, but now the circle has moved in the X direction one circumference. And if the radius is A, where it moved, the X coordinate moved half a circumference, because it went from here to here, so it went half a circle. Half of the circumference is pi A, pi times the radius, because the full circumference is 2 pi A. So the X value is moved over to 2 pi A, and whereas theta started at 0, your point was 0, 0 here. I wish they'd have put that in. Then when it's pi, X has moved pi A, Y has moved 2A. When it's moved another pi, theta has, yuck, the X value is now one circumference away, which is 2 pi A, but the Y value is back down at 0. Okay? Please show the curve. Okay, here it is. From this figure, you can see that the angle APC, and that's not a particular pretty angle, okay? It goes from here to there to there. Now, why they chose that angle, I'm not really sure, okay? But this angle here, A to P to C, is 180 degrees minus your theta. Now, theta, okay, it would have helped big time if I hadn't lost my pen. Okay, no, helped big time if they had shown that first circle here. Now my drawing's going to be terrible, I guarantee it, but that first circle here, the theta was 0. the theta is 0. The angle that it's turned is 0. Okay? So this would have been the circle something like here. Okay. And this is the point that you're tracing right here. So as this ball starts rolling to the right, this picks up from here and it's rolled a little way. It's rolled from, remember it started here, so your theta is going from down here to up there. Okay? If they had shown this point here, that's where the theta would have been pi halves. Okay? Because it would have started here and rolled up to there. They would have been pi halves. Okay? They didn't show that. They took it past there and it's rolled on to there. So your theta is that. So it's 180 minus theta, this angle APC. Now, why that angle? I guess there's a reason. I'll phrase it this way. This is a 90-degree angle. This is the complement of this angle that we're looking at. So this would be angle P, right there, the angle P, APC. That angle P is pi halves minus that portion right there. Okay? Pi halves minus, okay, theta minus pi halves. I think so. Anyway, it gives you 180 minus theta. It really is not all that good to try to squeeze this through. I'd say just look at this. Okay? X is A times theta minus sine theta. Now that's not entirely clear why that's the case, but it is. And Y is A times 1 minus cosine theta. Now you notice that Y is just going from 0 to 2 pi to 0 to 2a to 0 to 2a to 0 to 2a. So as cosine is cycling, when cosine is equal to 0, your Y is 0. When cosine is pi halves, then cosine theta is 0, and you would just be at A. And that's the one I was pointing out to you before. If they had gone over here, your Y would have been the value A, right here. Okay? And then when theta goes to pi, then you're up here at 2a. Okay? And then cosine at 3 halves pi, you're back down here at a again. Get out of there. Okay? Back down at a again, and then you're back down at 2 pi a there. So the Y is sort of easy to see. The X, man, that leaves a little bit of issue to do. And what they've done here is mix up degrees and radians, and that's what makes this sort of difficult. If they had just said this was pi minus theta, then I think this would have made more sense. Okay? But they threw degrees in there, and then down here they're talking in terms of pi. See, everything has pi's in it down here, but up here they're talking about degrees, which is not a very fair thing to do. So anyway, that is a cycloid. Okay. Now, why mess with this? Well, they mention here Galileo first called the attention to the cycloid once recommending that it be used for the arches of bridges. Pascal once spent 8 days attempting to solve many of the problems of a cycloid. I don't have 8 days. Okay, well, I guess I do, but anyway, such as finding the area under one arch and doing all sorts of stuff. They're not particularly that easy to deal with, but they have some really, really interesting properties. The cycloid has so many interesting properties and has caused so many quarrels among the mathematicians that has been called the Helen of geometry, and I'm not sure why Helen came into it, unless it was Helen of Troy and she caused problems. I don't know. Another name is the apple of discord. So there's further information here, math articles. Why did I read all that? Well, guess what? You could write a paper on cycloids, how are they used. You could write a paper on Galileo, how he fiddled with them, on Pascal, how he fiddled with them, and you'll just run into more and more people who spent more and more effort defining and talking about cycloids. Now, I don't know if they're going to do that here. I don't think they are. Yes, they are. Next page. Here's the deal. This is a nice smooth curve between here and here. But here you have a cusp. It's continuous, but its derivative is not continuous, because here it's going infinitely negative, here it's infinitely positive and decreasing. Here it's negative and getting more and more negative, here it's incredibly positive and getting less and less positive. So you have a cusp here, discontinuous first derivatives, but a continuous function. And that's why it's really a bear, really, to take areas under the curves and things like this. Now what we're going to do next, well, we'll get there. Hold on. Okay. So since sine of theta is equal to the sine of 180 degrees minus theta, okay, so basically what we're saying here which is the sine of that angle APC that we had, and that is AC over A, and it's also BD over A. A is your hypotenuse here, always. Goodness gracious, get out of there. That is your hypotenuse, and AC over A is the sine of this, and BC over A, no, that doesn't look right. BD over A, sorry about it. BD over A, yeah, AC and BD are the same, okay? And they're both the sine of the angle theta, okay? Or that angle, this angle up here. Sine of this angle, the opposite side over hypotenuse, which is also this side over hypotenuse, because these two sides are the same. That's all they're saying here. It seems like it's mucky muck, but that's what they're saying. Cosine is just simply now that is another issue. Cosine theta is minus the cosine of 180 minus theta, okay? And that's AP over A, which is if this is the angle, the adjacent side is this one, and there's the hypotenuse. So it's PA or AP divided by hypotenuse. Okay, so that's what that is. Only they put a minus sign because it's a minus cosine. So that implies that this, so if you want to follow this through, knock yourself out. It is not an easy process. Because the circle rolls along the x-axis, you know that OD, which is also the arc PD, So let's go back here. OD, that's the distance from the origin to this, any place here where this is AD. That's the first part of it, but then you subtract this off from it, the BD from it. So it's OD minus BD. But we already got what BD was right here. Okay, so BD is A sine theta. So, oops, OD is the arc PD, which is A theta. That's the key here because the x-axis depends on the sine, the y-axis on the cosine, and so that's why you get the A theta, which is an arc length, minus A times that. Okay, so basically, let's go back and see that. It's, you go out to here and then subtract that off of it. So that's what you were just doing there. This OD minus BD. Okay, and that's what I have, OD minus BD, and that was the arc A theta minus that BD, which was the A sine theta. Your Y is just BA, which is A minus A cosine theta. So the parametric equations are those, and you can factor out the A from both of them. A times theta minus sine theta, and Y is equal to A times 1 minus cosine theta. Okay, rather bizarre parametric equations. Okay, so the cycloid in that figure has sharp corners called cusp at the values x equal to n pi a. Okay, and notice that the derivatives there are both 0 at the points for which is 2n pi. So therefore you have an indeterminate form, well, not quite the same, but both the change of x and the change of y with respect to theta are 0. Okay. Boy, they're just beating this in the ground. So there's your x as a function of theta. There's y as a function of theta. Your x prime, the first derivative of that, is this. The first derivative of this is that. And the first derivative of that one is 2n pi, that 0 and that 0, because cosine at 2n pi is 1, so this is a minus a, and sine of 2n pi is always 0. Okay, between the points the cycloid is smooth, and here's the definition of a smooth curve. A curve C represented by x equal f of t, y is equal to g of t on an interval I is called smooth when f prime and g prime are continuous. Notice this one is not, okay, at those cusps, is everywhere in between on I, and not simultaneously 0, which these turns out to be at those points, except possibly at the endpoints of the interval, which is where these are. The curve C is called piecewise smooth when it is smooth on each subinterval of some partition I, which this was. Now, if that wasn't enough, flip over to page 706 and you hit the totochrome and brachistochrome problem. And these, if you thought cusps were bad, these are equally bad. Okay, the cycloid is related to one of the most famous pairs of problems in the history of calculus. The first is called the totochrome, I think is how you pronounce it, problem. Began with Galileo's discovery that the time required to complete one full swing of a pendulum is approximately the same whether you make a large movement at a high speed or a small movement at a slow speed. Approximately the same. And what's happening there, you're moving approximately on the path of a totochrome. Now what the toto means is same, chrome means time. The same time happens. Okay? Galileo realized he could use that principle to construct a clock. So Galileo not only was the one who started with Newton's first law, principle of inertia, he also invented the first clock. He made a great improvement in the earliest telescopes, so you could see far better than you ever had before. He was quite, not just a physicist, he was quite an engineer as well. However, he was not able to conquer the mechanics of the actual construction. Okay? Christian Huygens came along much later, almost 2 centuries later. He was the first to design and construct a working model of a clock. He realized that the pendulum does not take exactly the same time to complete swings of varying lengths. But in studying the problem, Huygens discovered, here's another paper topic here, Huygens discovered that a ball rolling back and forth on an inverted cycloid does complete each cycle in exactly the same time. So rather than having a pendulum, which basically is making an arc of a circle, okay, flip over a cycloid, and then that's not quite the same as the arc of a circle. A ball rolling back and forth in that, when you flipped it over, it's going to complete every one of those rolls in exactly the same amount of time. Whether you start here and go the full way there, or start down here and do like that. Well, you can't see that, I'm sorry. Whether you start, now flip this over, and whether you start here and go like this, back and forth like this, same time as if you started here and went back and forth like this, along that inverted cyclone. And the reason is, up here you get more speed to begin with, incredibly more speed, but it still takes the same time to make one complete arc. Whereas here you have very low speed, and it takes exactly the same amount of time to do one arc. Okay. The second problem, which was posed by John Bernoulli, and if you take a look at him, he looks like he wasn't the most pleasant of characters. His picture's in the book there. In 1696, so you see this was the year after Huygens died, in fact. Okay, it's called the Brachistochrone problem. In Greek, brachis means short, chronos means time. The problem was to determine the path down which a particle will slide from point A to point B in the shortest time. Okay, now that's sliding rather than rolling. Okay, the solution is not a straight line from A to B, but an inverted cycloid passing through the points A to B. So actually you go, the quickest time is to give it a big speed at the beginning and then let it ease on down here. Okay, if you just do a line down here, that's not the quickest. This is the quickest, even though it rolls further. Okay, that's shortest time. The amazing part of the solution to the Brachistochrone problem is that the particle starting at rest at any point C in between A and B takes exactly the same time, which is basically your Todochrone problem again. If you start here, it gets a huge speed to begin with, slows down this one, it starts slower. It's going to take the same time to get from A to B as it will to get from C to B. Incredible, but true. And that's it. We don't have to do any with it, but that's your inverted cycloid. Okay. Homework, any questions on 10.2? Don't sweat that last part too badly. I don't think you'll see any problems on those, and hopefully you won't run into any in your lifetime, but if you do, at least you've been exposed. Now, I don't always say this, but the concept check at the beginning of each set of exercises a really good thing to look at. It just refreshes in your minds the concepts this section has been talking about and puts it out there for you what you need to know. But then the homework exercises, any of the odds 5 through 21, they're all at Calc Chat, 13's at Calc View. Any of the odds 23 to 33, they're all at Calc Chat. 25 is at Calc View. Any of the odds 35, or either 35 or 37, they're both at Calc Chat. 39 or 41, they're both at Calc Chat. Any of the odds 43 to 49, they're all at Calc Chat. And then 51 or 53, they're both at Calc Chat, with 53 being at Calc View. Then either 55 or 57, both at Calc Chat. 55 is at Calc View. Then any of the odds 59 through 65, they're all at Calc Chat. And you'll see a couple of other names there. The Witch of Agnesi, which is really a terrible name for that. Agnesi was a woman, one of the few early, really good, famous female mathematicians. She came up with some problems, some issues that she threw out there that people had a lot of difficulty with. She didn't. She was really bright. And they called that, because of a translation thing, it was something that should have been translated curve or something like that. They got a vowel or something wrong, and they used the word that they meant rather than curve. Very, very similar word meant witch. So they named it the Witch of Agnesi because it was a tough problem proposed by a woman. They made it a witch. Not nice. And Folium of Descartes. So there are several more potential paper topics there. So do any of the odds 59 through 65, but you can use any of those as potential paper topics. 67 or 69, you can explore doing those, think about those. 71 or 74, they're both at Calc Chat, all the odds are. They mentioned there the curtate cycloid, or on number 64, which you didn't have to do, but 75 is talking about that, and so you can look at that one if you'd like as well. Okay, it should be at Calc Chat. There's a couple true false, 77 and 79, they should be at Calc Chat. 81 should be at Calc Chat. A good old baseball problem there, Kyle. Okay, and that's it. That's the end of the section 10.2. They do some things. I don't know if you remember the old, I can't remember what it was. It was a thing that you could put a pencil in and draw circles around, and you came up with all these neat patterns. That's basically what they're doing here. Okay, only this is computer generated. All right, let's move on to 10.3. How are we doing on time? We've got some time here, so let's get out of this slide and go to 10.3. Now, I had opened it up, and as it sometimes happens, it won't show up. Okay, so what I've got to do is figure out a way to get it open again. There's 10.3. Now let's go back to Zoom and see if it'll pull it up now. It won't here, but let me now do, there it is. Okay, it's so weird how Zoom, you have to do the things in the right order or it won't work. Okay, so here we are. Get the slideshow from the current slide, and I'm also going to have to move my taskbar around, so let me get that out of the way. Okay, drag this as far to the bottom as I can. Okay, so chapter 10, we're not doing the conics part, that was 10.1. Parametric equations, which was 10.2 and 10.3, which we were getting ready to start, and polar coordinates, which is 10.4. Good buddy. So here's 10.3. If it will advance, it won't until I click on it. 10.3, parametric equations in calculus. Hey, that's what we've been waiting for, isn't it? How are these related to calculus? What we're going to do here is find the slope of a tangent line, good old calculus problem, to a curve, but this curve is not y as a function of x. This curve is one given by a set of parametric equations. We'll also find the arc length of a curve given by a set of parametric equations, not y as a function of x. And we'll find the area of a surface of revolution in parametric form. Okay? So let's get going on that. Let's start with slopes and tangent lines, not of curves, y as a function of x, but of parametric curves that are defined by parametric equations, a set of parametric equations. Let's consider the projectile represented by the parametric equations. X is equal to 24 times square root of 2t. Excuse me just a minute. I'm sorry, that's not very satisfying. I need something to wet my whistle. Okay? Now, y is equal to minus 16t squared plus 24 root 2t. Now, I don't know if you remember this, but this was exactly the set of equations that define an object launched at 45 degrees with a horizontal. So its initial velocity was along the bisecting angle here, 45 degrees. So its x component of the velocity was, and I believe it was 48, velocity of 48 feet per second, meters per second, whatever. I think it was that short fly ball that Kyle hit. You know, it was an out, but you know, it was good effort though. Okay, I only hit it 48 feet per second, which is pretty slow. Here was the y component. Gravity was always pulling that thing down, unfortunately, and that was 1/2 the acceleration due to gravity, which in feet per second squared is 32 feet per second squared. 1/2 that is minus 16 because it's downward, t squared. And then this is the y component of the initial component of the velocity was 24 root 2t, just like the x component was, because at 45 the x and the y components are the same. Okay, you know that these equations enable you to give the position of the projectile at a given time. You also know that the object is initially projected at an angle of 45. That's where the root 2 came from. Square root of 2 over 2 is the sine and cosine of 45 degrees. And if this started at 48, multiply that by square root of 2 over 2. 2 in the denominator cancels 48 into 24 times root 2. So that's where that comes from. Okay? And of course, at angle of 45, the tangent is 1. Don't know why they brought that up, but it's true. Okay, but how can you find the slope at some other time, t? This next theorem answers that question by giving a formula for the slope of the tangent line as a function of time, not as a function of x. See, what we want here, the slope of the tangent line here to be a function of t, not a function of x. So here you have it. Parametric formula of derivative. If a smooth curve C, which that was, nice smooth curve here, no cusp or corners in it, okay, nice smooth curve. Smooth curve C is given by these equations, x equal f of t, y is equal to g of t. Then the slope of C at any point xy is, of course, dy dx, but what is dy? It's dy dt over dx dt. That's exactly what it is. So all you do, now that's, as long as that derivative of x with respect to time is not 0. Okay, so the x speed, you might say, can't be 0. And most of the time it isn't. If your x component in this direction is constant, if that constant was 0, not going anywhere. So if it's any given initial velocity in the x direction, it's always going to have a velocity in the x direction. So that's not equal to 0. So let's do what they said. Find dy dx for the curve given by this set of equations. What we just learned was, let's do dx dt. Anyone tell me what that is? If x is sine t, what's dx dt? Cosine t. Derivative of sine is cosine. What is dy dt? You did it earlier, somebody. Minus sine of t. Okay? Derivative of sine is cosine. Derivative of cosine is minus sine. Okay? Now, so what is dy dt? dy dx, the slope at any point x. Okay? This is dy dt over dx dt. Just about like you should expect it to be. Okay? And that would be dy dt is minus sine t over cosine t, which is minus tangent t. Okay. Man, I got something, get something else to drink. Hold on. Like I said, I crammed down my salad without drinking enough fluid, and it's getting to me now. So there is your slope at any time t, dy dx from that. Well, but wait a minute, don't we need that back in terms of x's? I'm not sure we do, and even if we did, not going to be a very easy thing to do. Let's see what the book does, if they bring it back to x's or not. There's your solution. Dy dx is the y dt over dx dt, just what I have there. That's minus sine t over cosine t, which of course is minus tangent t. Now, do they leave it there? Yes, they do. Okay. They don't try to go back to x's. Okay. So that was example 1. Now, that's all there is to it. Don't try to make anything else of it. Let's see what follows that. Because dy dx is a function of t, you can use theorem 10.7, which was back the one we just used, repeatedly to find higher order derivatives. For d2y dx squared, the second derivative of y with respect to x would be d by dx of dy dx. Well, the dy dx is oh goodness. It's okay. D of dy dx, that's what with respect to t, over dx with respect to t, dx dt. Okay? Now, they don't take it any further, which is sort of a shame. They kind of leave it hanging there. That's an awkward form to leave it, because you see you still got x's in here. If you could get rid of the x, then that would be very good. But you could, because if you remember this, dy dt is dy dt over dx dt. Okay? So you can usually get rid of that. The third derivative of y with respect to x is d by dx of the second derivative, so it's d by dx of this thing here, which was this thing there. Okay? and well, actually, it's just doing d by dt of this thing over dx dt. So basically, they're just doing another derivative there. What you do with this one is plug the first derivative in and you get it. Once you get that, you plug that second derivative in when take the derivative of that with respect to t. This graphic leaves a lot to be desired. Okay, they are showing you the simple first step but not taking it any further. Now that leads to, it doesn't lead to example 3. We need to do example 2 first. Okay, how are we doing on time? We've got about 8 minutes. Let's see if we can knock out example 2 then. So let's get our screen share set up to the whiteboard. Let's clear the whiteboard, and for some reason all these things came back down. So let me move it back up as much out of the way as possible, and we can go from here. So let's do example 2. For the curve given by, my clip is falling off my headset. Okay. Yuck. Now I don't know what just happened. Okay. Let's go back. All right. Here's a set of parametric equation. X is equal to, now I'm going to save a step here. They say the square root of t. I'm going to write that as t to the 1/2 power. I don't like dealing with square roots. Okay. Here's your second parametric equation. Y is equal to 1/4 t squared minus 4. Okay, and here's what t is. T is, get out of there. T is greater than or equal to 0. All right. It's asking for the slope and then the concavity. Whoa, okay. So let's see first if we can do slope. What is slope? Slope is dy dx. Okay? Alright. Dy dx is dy dt over dx dt. Okay? So that means we're going to take a derivative here. Dy dt is going to be 2 times 1/4 is 1/2 of t. So it's t over 2. The 4 doesn't contribute anything. Dx dt, on the other hand, is simply 1/2 t to the minus 1/2. Okay? Now, write the ratio of these two, and notice that you have a 1/2 there and a 1/2 there. So basically your 2's are going to cancel out. Okay? And that leaves you t over t to the 1/2, which is t to the 1/2. Okay? Now, no, it isn't. Oh, I'm sorry. This was over t to the minus 1/2. So you flip it over and it's t to the 1/2. T times t to the 1/2 is t to the 3/2. Okay, sorry about that. T to the 3/2. Now, that's the slope at any time t. Okay? And we can leave it like that because that's your independent variable t. Now, the concavity, and it said at point 2, 3. Okay? When x is equal to 2, that's supposed to be t to the 1/2. So you square both sides and you get t is equal to 4. Okay? Let's do the same thing here, and you get y, if t is equal to 4, 4 squared is 16. 16 minus 4 is 12. 1/4 of that, so y is equal to 3. And that sure is the point they gave you. X equal to, y is equal to 3. So that works when t is equal to 4. Okay? Well, the slope then would be 4 to the 3/2 power. Now the way to do that in my mind is take the square root of 4 is 2, cube that, and that would give you 8. Now they don't give any units here, but the slope is 8. Okay? They show the picture here, and you see that is indeed what you got. We got 3 minutes left. Let's see if we can calculate d2y dx squared, and that will give us the concavity. So d2y dx squared would be d by dt of dy dx okay, over dx dt. Okay? Now, we already know what dy dx is. So this is this one, d by dt of t to the 3/2 power divided by dx dt, we found out was 1/2 t to the minus 1/2. Okay, you wind up with a minus in the denominator, and it looks like to me this comes up a 1 over 1 over 2 would be 2, and this would be, this moved up top would be t squared. And remember we said our t was 4, so this would be 2 times 16, which is 32. What's the concavity there? Concave up. Now they had it 12 and I have 32. I must have messed up something somewhere here. Okay, let's see if I did. D, this is D of 3/2. I got that part over 1/2 that. Oh, I forgot to take the derivative of that. Sorry, that's it. No wonder. Derivative of this is 3/2 t to the 1/2. And that's what we divide by 1/2 t to the minus 1/2. And again, the 2's go out. Oops, 2's go out, and that gives you 3, and then this one flips over and becomes 3t. Okay, so then not 2t squared, 3t, which would be 3 times 4 is equal to 12. Okay, and that is greater than 0, so it's concave up. All right, sorry, sort of messed that one up. And I think I went a minute over in that file up there, but guess what? I won't do any extra charge today. Okay, we'll be beginning next time with example 3. So let me get out of this for right now and go back to my PowerPoint. and go from current slide, and that's where we'll be starting next time. Example 3, top of page 712. Okay. Alright, let me see if we can get any homework problems out of this. I hope we can. Oh, we're almost there. I think you can do either 5 or 7. They're both at Calc Chat. 5's at Calc View. You can do any of the odds 9 through 17. They're all at Calc Chat. 13's at Calc View. I think you can do any of the odds 19, either 19 or 21. They're both at Calc Chat. 19's at Calc View. And do either 23 or 25. They're both at Calc Chat. Hold off on the next part because that is finding a curve with 2 tangent lines, and I think that's what the next one is doing. We'll do that example next. Any questions? All right, we made decent progress in 10.3. That means we only got 10.4 to go before we're ready for the next test. Think we'll be there by next week at this time. So that means use the weekend wisely, folks. I would say really be working on that first test. Okay. If you need more time, you can still have it out after I give you the second test, but I say that for your benefit so that you don't have 2 tests out there at the same time and you're getting further and further behind. So try to get the first test wrapped up this weekend if possible and get it in to me sometime over the weekend or early next week will be fine. Okay? Any questions? Okay, I'm going to stop sharing if there's no questions. And unless someone comes up with something, I'm going to end the meeting for all of us. So any questions? Looks like we've already lost maybe one. Yeah, we've already lost a couple people. So take care. We'll see most of you, or 3 of you, a little bit later this afternoon. And I'll see the rest of you next Monday. Have a good weekend. I'll see those same 3 on Wednesday. Okay, on tomorrow. Okay. Take care. Bye-bye.